So with that, I really want to get us back on track. So we're going to start with our first presenter, Dr. Hiba Baroud. Oh, you're right in front of me. No wonder I didn't see you. Welcome, Vanderbilt University. Come on up, let's get the day started.
All right, good morning, everyone. I'll try to get the time back, so I'll make sure that I finish on time or maybe a bit earlier. My name is Hiba Baroud. I'm an associate professor of civil environmental engineering at Vanderbilt and also serving as the interim director for the Vanderbilt Center for Sustainability, Energy, and Climate. Really happy to be here. And what I'm going to talk to you about are the finances side of resilience and adaptation. There's a lot of talk about the benefit of investing in resilience and adaptation. Unfortunately, this is actually not happening on the ground. And so we're going to unpack what are the reasons behind this and the work that we're doing in my group to address these challenges. So a brief kind of step back to just make sure that we're all on the same page. The way we define risk is an interaction or a combination of hazard and resilience/vulnerability, meaning that if I improve my resilience, I can decrease the risk from disasters. And the cartoon here is showing the 4 pigs with different levels of preparation shown by the different types of shelter that they built to protect themselves from the tornado. So the stronger, the more expensive, but also the better protected you are against the hazard. So that's kind of the basic idea. And when we think of adaptation, it's also along the same lines. Climate adaptation and mitigation also contribute to enhancing resilience and decreasing that risk. There's been some actual numbers put into this concept that I just described, meaning that, okay, if you put in $1 or this much money towards mitigation or resilience, you're going to get back some of it. So, or actually more, you're going to get back $13 savings in terms of damages, recovery costs, and economic impact. And this work has been shown not just in research. A few papers have done, or a few studies have explored this, but also among organizations and in the practice. The 2024 Climate Resiliency Report from the U.S. Chamber of Commerce highlighted this kind of this ratio, the cost-to-benefit ratio, but also the National Institute of Building Sciences in their Resilience Incentive Roadmap 2.0 also highlight the importance of investing in climate resilience. And these are not the only numbers. There's also a lot of other ratios that have been calculated. This one is by the UN Disaster Risk Reduction, where they differentiate between investment and risk reduction and prevention that brings savings towards post-disaster recovery versus how much we get in terms of investing in making infrastructure disaster resilient, and that saves on reconstruction. The challenge, though, even though that we can see the benefit of investing in resilience, and there's all these kind of statistics that have been demonstrated here. In reality, this is actually not happening. So although the benefits are clear, there's very little percentage of financing that goes towards disaster resilience. And I'm just gonna show just kind of one example here that came out from the Global Assessment Report on Disaster Risk Reduction. So this shows how much money goes towards official development assistance, or ODA. So ODA is kind of like a government aid that comes from wealthy countries towards the development and improvement of welfare in developing countries. So just to give you a sense, that gray circle at the top, this is total ODA funding that was spent between 2010 and 2019. The little green circle is what actually went towards disaster financing. Then within that little green circle, there's just a sliver of gray that 4% is going towards actually disaster prevention and preparedness. So even though we know that this makes sense and it helps a lot, yet there's a lot of resistance and reluctance towards actually putting money towards disaster resilience, putting money towards climate adaptation. So why is that? We can see that, the science, the data back up and identifies the importance of doing so. But when we look at actual actions, this is, for example, one study that looked at Louisiana. They see that there's actually not enough that is being invested to improve disaster resilience. There's also, this has been pointed out by practitioners, that there's, no one is really interested actually in putting more money towards climate adaptation. There are two reasons for this outcome. The first one is related to money, and the fact that there's investing in disaster resilience requires very high upfront costs. And the return is not clear on that. To put it very simply, a water engineer, I like this quote that is mentioned in a post by the State of the Planet. A water engineer said, investing in resilience is a tough thing to convince people to do, because when you invest in resiliency, the payoff is that nothing happens, which is not very exciting. Putting it from an investor's perspective, it is seen as an opportunity cost. So you're paying money, but really there's something, the benefit that you get is protection from a very extreme rare event. The other issue is also related to the fact that those who are investing are not the same people who are benefiting from that investment. And in fact, in that NIBS resilience incentivation roadmap that they published in 2023, they do mention this issue, is that whenever there's a clear benefit, when you have natural hazard mitigation, saving, a few dollars for society against the $1 that is being invested. But truly, when it comes to buildings, it's the owners and the builders that are bearing the cost, and yet they enjoy only a part of the benefit. And so this is what is contributing to that kind of investment gap. Which brings us to the second reason why there's that investment gap, which is related to cognitive biases. So if me as a person, I'm putting money for something that someone else is going to benefit, what is really the incentive for me as a builder or as an investor or as an infrastructure developer? Why would I put in the money if someone else is going to benefit? So that brings up a lot of issues related to challenges in cooperation and social dilemmas. So some people are paying the bill, while others are being we think of them as free riders. This is actually also highlighted in that cartoon. I'll go back to that first slide that I showed. If you notice, the fourth pig is actually inviting the other three pigs to join in on the very strong shelter that was built. So why would, although that fourth pig is the one who put in all the money to build that shelter, the other three pigs are going to just benefit and free ride on that investment. So again, this as a result does not incentivize people to put in money there. So what I'm going to spend today's talk is to show you the research that we're doing to address these two challenges. The research problem related to these two challenges, on the money side, the issue is that we're not doing a good job of quantifying that benefit on investing in resilient infrastructure. The benefit goes way beyond that single building or that single infrastructure that we're developing. There's a lot more interconnected systems. It's a very complex network, and they're all benefiting from this. So we need methods that allow us to quantify this return on investment and assess the direct and indirect benefits as well. I'll spend less time on the decision side, but I will show an example of how we address this. But the goal here is that first we want to be able to predict how people are going to make decisions in situations where we have these issues of cooperation. So when we have a situation where we're all in here, we can all pitch in to protect ourselves from an incoming tornado. How much money do we put in? What affects our decision behavior? Is it related to personality traits? Is it related to the environment or the decision process that we're in? And so the goal here is to be able to, in a way, use data-driven methods to predict the behavior of decision makers, but also identify factors that contribute to these behavioral patterns. I do realize we are in a building community here. The case study, though, does not cover buildings. My work is related more to infrastructure and lifelines, and so the work is going to focus, the case study that I'm going to show will demonstrate investment in port infrastructure. and how that affects the supply chain and system resilience of the entire inland waterway system or part of it and along the Mississippi River navigation system. But the proposed approach that I'm going to talk about is very general and can be applied, and the goal for it is to be applied across multiple infrastructure sectors as well as buildings, thinking of them as part and asset of a big network or big multi-connected or interconnected system. So to tell you a bit more about the case study, I'll just take a step back and tell you a bit about what motivated this research. This was part of a national disaster resilience competition that was announced in 2014 to help U.S. communities recover from prior disasters and think about resilience for future disasters. And so one of the winning teams was in Tennessee, and the goal was to investigate the resilience of the supply chain along the Mississippi River. And specifically, our main task, which initiated all these research questions that we were interested in later on, was to evaluate the impact of making investment in waterborne infrastructure on the resilience in the whole region. So if I improve resilience in one or two key areas along that system, how does my entire resilience and my entire regional resilience improve? So to tell you a bit about inland waterways, they are the backbone of the U.S. economy. They transport hundreds of billion dollars worth of freight annually. They are a safe, low-cost, and environmentally friendly mode of transportation. This figure here is showing a 15-barge grain tow. This is equivalent to about 1,000 trucks taken off the road. So it's cheap and it's safe for the environment. So it should be a good or kind of superior freight mode, except that it is actually, this mode is quite vulnerable to natural hazards, primarily floods and droughts. So a couple of specific events in this region. In 2019, sections of the upper Mississippi River was closed for months due to flooding and led to more than $1 billion in losses and worth of grain that is not shipped. And then in 22, the other extreme happened where drought also halted commercial traffic for more than a month, and again, several hundred billion, more than $60 billion in loss in economic activity. So there's that issue here, and so the challenge is to figure out, well, is there a way to mitigate or avoid these losses in the future to make inland waterways kind of an opportunity to enhance resilience in that region and also at the same time benefit from the other advantages of that mode. So one possible solution was to add a port or build a port that would help reroute some of these shipments that were halted. And in fact, that port was built. It's the port of Kate's Landing, and it's that orange dot that you see at the bottom, at the mouth of the river. It's on the kind of like on the Tennessee, technically, side of the river. And it was built to be resilient to 500-year floods in certain parts of it, and to kind of give you a context, the event that happened in 2019, that was a 100-year flood. And so really very forward thinking about future climate change and future disaster intensities. And so again, the plan was to, handle rerouting shipments, and then that would help potentially mitigate those economic losses that were experienced. The considerations here was that, building the port in itself is not enough, because we want to see how the system is going to respond to this. What are those uncertain scenarios? How are those losses going or shipments going to be rerouted? Will shippers actually choose that option? So there's a human component here. And then what are the cascading effects of these disruptions throughout the region? And so you can see that there are a lot of questions. Some are economic, some are on the risk analysis and infrastructure side, and some are on the human side. So there's really a need for a true interdisciplinary approach that addresses all these sides of or aspects of the problem. And this is our proposed approach, which, like I said, it's general, but in this case, I'm going to describe it in the specific case study of inland waterway. But it can be applied across the board. So it covers hazard modeling, it covers risk analysis, the human decision-making, the shippers deciding whether or not to ship, the economic impact, and then we assess this whole kind of economic impact with and without having the resilient port there. So I'll spend a few minutes briefly walking over the different components of the framework without getting too much into the details. But if you're interested in more details, of course, I'd be happy to talk to you. And there are papers also cited or linked in the slides. So for the flood scenarios, again, like you saw, there are a lot of extreme events. It could be a tornado, it could be a flood, it could be drought, it could be earthquake. But the idea here is that the hazard modeling has to be done in a probabilistic way to account for different scenarios. And so our approach here, what we did is the goal was to evaluate the expected number of days those sections of the river are going to be closed under a certain flood intensity. So we use the Waterway Action Plan, which determines thresholds beyond which a section of the river should be closed due to high water condition. And we combine this with historical data on the daily river stage. And we use a probabilistic model to represent or to model the number of days or expected number of days that are going to be closed under different flood scenarios. And so we explored multiple distributions, but here we chose the Gumbel distribution, which is it's a form of a generalized extreme value distribution. And the nice feature of it is that the quantiles of this density can be used or can be interpreted as return periods. So for each return period, we have the expected number of days of closure. Again, this is all based on historical data. So now that the hazard has happened, what is going to result in terms of the port disruption? How is that going to impact the decision process? The idea is that there are various decisions that could happen. So we can either wait out until the water levels have come back to a safe level, but this also is what resulted in a lot of perishable goods to go bad in the case of the 2019 flood. There are other decisions where shippers could actually reroute to another mode of transportation, which is typically what is done. So reroute to rail and truck, but that is more expensive. Or with the port, the other option is to reroute through the resilient port if it's there. So to model that decision process from the shipper's standpoint, we use an agent-based model that is parameterized with various parameters that kind of describe this trade-off. So here are a couple of parameters. The beta is a discount factor for on-time delivery. So this is kind of the cost that you pay, but to ensure an on-time delivery for shipments. Whereas the alpha is that penalty fee in case the shipment was delayed or in the event that the goods are perishable and are going to result in a loss if they are not shipped. So now that we've done this decision process, what is the outcome or the impact of that decision? Whether the shipment is late, or if it's gone bad and never delivered, what are the economic impacts? Again, those economic impacts, when we think of them from the shipper's side, there's a cost to the shipping company, maybe to the organization receiving those shipments. But truly, the actual outcome or the actual impact goes beyond that initial direct loss. It goes to other economic sectors that rely on these shipments. And so for this, we use an interdependency economic input-output model, which allows us to link all the economic sectors together. And this is based on the Leontief input-output model, which kind of conceptualizes the way different economic sectors are linked. So we have Q is a vector of production inoperability, meaning that the loss that I experience from the delayed shipment or the lack of shipment results in a decrease in production. And then it links it to demand perturbation as well. So it basically shows how the economy is going to be imbalanced as a result of a disruption in the economy. How are these all linked? They are linked through an interdependency matrix, A star, which links all these economic sectors. So think of A star as like a kind of like 50 by 50 matrix. Each row refers to one sector in the economy, and the number in there refers to how they are related, meaning that one economic sector, very simplistic example, one economic sector could be like, I'm interested in the shipment of tires, and I'm concerned about how the delay in shipment of tires is going to impact the production industry of cars, okay? And so it gives me a sense of how connected these two economic sectors are. There's been various extensions to this base model. The one is the dynamic version of it, which not only models that cascading impact, but also models the recovery process. And then the model that we used also looks at, in addition to the dynamic recovery, also looks at multi-regional. So here, in the previous version, the K-star looks at the interdependency matrix controlling the recovery, so how much the recovery of one economic sector is going to improve the recovery in another economic sector. And then T-star is also another kind of interdependency matrix, which looks at how the losses in one region cascade to the losses in another region. And so that's kind of, if you going back to what I mentioned, the importance of accurately describing those benefits. This is what it is. We need to look at beyond this one building, beyond this one infrastructure. The presence of this resilient infrastructure is benefiting a wider circle outside of this particular building being resilient. And that's what we're trying to capture here by going beyond kind of this first initial shipment of grain that was not shipped, beyond this particular state, looking at multiple states that were impacted. So back to our approach. So we look at the flood scenario. So the hazard scenario is uncertain. That decision process is uncertain. Determining those parameters also is uncertain. And then as a result, economic impacts are uncertain. So there's quite a bit of uncertainty. How do we quantify or address that uncertainty and propagate it throughout the system? We propose to use a Bayesian approach, which allows us to, it's a class of statistical models that allow us to estimate our variables in probabilistic terms as opposed to deterministic. So instead of looking at one expected economic impact, one number, we're looking at a distribution of possible expected outcomes. And that distribution is a function of the various hazard scenarios, the various ways a shipper might make a decision, even our model uncertainty, like our decisions, our assumptions of what these parameters are. So it takes into account all this uncertainty and puts it into a distribution form. The challenge is with what we have here is that we're using an agent-based model, and parameterizing ABMs can be quite complex. And so those complex simulations are they're not compatible with traditional Bayesian inference or maximum likelihood estimation, because these typical methods require a well-defined likelihood function. And in the case of decision models like ABMs, the likelihood function are either unknown or intractable. So instead, we propose to use a approximate Bayesian computation, which is sort of thought of like a likelihood-free approach. And the way it works is that we sample from various parameter values and compare it to observed data. And if the samples are within a certain threshold of that observed data, then we retain that sample and we use it to inform the posterior probability distribution. So the posterior distribution is that kind of predictive probability distribution of those economic impacts that account for all these uncertainties that I mentioned. We use the 2019 event as a calibration. Like I mentioned, it's a 100-year event. So here, this shows the, instead of kind of like that there was $1.2 billion worth of agriculture or grain that was not shipped. Here, instead, now we have a distribution of the amount of agriculture that was not shipped across different assumptions of alpha and beta. Remember those two parameters that control the decision process. And then you can get a sense of how accurate we are or how close we are to the reality in our model. So let's look at some results. So first we look at production losses across different scenarios. So the four quadrants here are showing different flood return periods going from 20-year to 500-year. And then the x-axis are the different states that could be impacted by these events. So those are the states that are along the Mississippi River that receive or ship goods along that system. And so we noticed that Illinois, Missouri, and Minnesota are all impacted highly. There's quite a bit actually of shipping activity from the upper Mississippi River southbound. Louisiana also is impacted because Louisiana receives a lot of shipping. And so, and then obviously the more extreme the event is, the higher those losses, but also the more uncertainty we have. So those are box plots. And so the wider that rectangle, that box plot is, meaning that there's more variability and uncertainty in my estimation. when we first started working on this project, really the basic question was, just tell us the cost-benefit analysis. Did this port kind of pay off for what it cost? And so you may not remember, I mentioned it a little bit in my initial slides. The actual cost of the port was $55 million. And so we were curious about, at what point do I break even, depending on the cost of that port. And what we find out is that when looking at all those economic losses, really the break even is 30-year event, meaning that if I experience an event that is stronger or more intense than a 30-year flood, I'm already getting that payment back on this port. The question is, who am I? Who is actually the person getting that payment back? Well, that depends, because we look at those production savings. So now we add the port, the resilient port, and we look at how each state is actually benefiting from the existence of that port. And we noticed that Illinois is actually the one that saves the most in a way from having Kate's Landing, that port of Kate's Landing being there, while Tennessee has very marginal, almost non-existent. So we can think of, now of course, investing in these large complex infrastructure, there's federal funding, but there's also local funding. And so the kind of thinking about it, the port sitting in Tennessee, but really Illinois is the one benefiting the most from that infrastructure. And so thinking of Illinois could be a free rider in this case. But this brought up this whole decision and cooperation biases. Like, why would someone be interested in, if we think about those states as individual decision makers and Tennessee putting money towards improving resilience, but really the beneficiary of that resilience is someone in Illinois. So shouldn't also Illinois pitch into that kind of public good? And so this is where we started to look at that decision process, this rerouting option. It's not just up to the shipper's side, but also there's a decision related to how much we're investing initially in that port infrastructure. I won't spend a lot of time on this, but I just do want to mention kind of the work that we've done. So we did kind of an experiment where we designed an online game. And we had participants, we're given kind of like a disaster situation, and participants were expected at each turn in the game to put in money to protect their community. So they're putting money towards building a shield to protect their communities. And they're playing against a computer, and that computer is more going towards a kind of equal or more fair share that we call the Pareto efficient. So the one shown here is where the computer is instructed to contribute an amount that is proportional to how much they would benefit from that shield or that shelter. So we used the data that we collected from the online game to build a statistical model and learn about what contributes to people either over-contributing or under-contributing money towards that public good. So we had them fill out surveys about, the big 5 personality traits, and we had also some other information collected related to the environment of the game, but also the demographic. And the model that we built is a tree-based model that looks at nonlinear relationships between personality traits and the willingness to put money towards this public good. And so we use a Bayesian additive regression tree, but also compare it to a multiple linear regression, which is typically what is found in the literature, looking at kind of that linear relationship between those factors. But in our model, we found that there's actually quite a bit of nonlinear connection between those. So the BART model, that tree-based model, provide really accurate results in predicting the decision based on these personality factors. And then we wanted to see, okay, well, which personality factors actually influence that decision. So we looked at variable importance. We did some statistical tests that are shown at the top. And also we looked at partial dependence plot, which these partial dependence plots, they summarize that marginal effect that a specific set of input variable has on the response variable, while of course controlling for the other input variable. So our response variable here is that deviation from the computer decision, from the Pareto front. And so that deviation tells me if you are over or under contributing. And so one of the most important factors is a personality trait referring to openness. And so openness is kind of measures the pro-social behavior, how much a person trusts others. So higher score refer to pro-social behavior, but it's also about kind of intellect and general intelligence, or the ability to solve complex problems. And so the higher open scores are predictive of participants who will play the game closer to a Pareto efficient strategy. And we see that the higher that score is, so in the partial dependence plot, the one on the top left, part A, is showing how the changes in the openness score change that willingness to contribute. And so they have a tendency, actually, the higher openness score have a tendency to under contribute towards resilience. But again, there's a lot more details on this, and the goal for us kind of in the next steps is to add this kind of the outcome from that machine learning model to inform that agent-based model. So use more kind of empirically based or data-driven parameters as opposed to making assumptions about those parameters that influence decision-making. Another addition that was recently made was, remember I told you about the flood scenarios, we looked at historical gauge levels. And so, but the reality is we want to be forward-looking. And so we added kind of the climate projections to look at future climate scenarios and how flood events occur in the future under various scenarios. So we followed the same process in terms of looking at the number of days a certain section of the river is going to be closed, but we do this under 4 different climate scenarios that represent various levels of emissions. And then again, so now we have 4 climate scenarios and then each of the flood intensity levels. And we use that to, again, look at the savings. So on the left-hand side, I have the production losses, and then on the right-hand side, I have the production savings from having the port here. And we do this for each of those climate scenarios. Generally, which was we expected that the closures tend to increase when we have higher degrees of warming, which was generally the trends also that is observed in savings and losses, with the exception of a couple of climate scenarios where the temperatures are so high to the point where we have less snowfall. And so as a result, this means that there's less water melt, and so that there's less risk on the river flooding. So there's kind of that trade-off between, okay, there's increased precipitation, there's increased warming, which increases some of these occurrence of these high precipitation events, but at the same time, what contributes to flooding in that region is also driven by snow melt from upstream. We also noticed that having the Port of Kate's Landing is able to mitigate impacts of floods across all scenarios, but when the scenario becomes too extreme, these savings are generally capped, and that cap is due to the port capacity. Another thing that we were interested to look at is industry-specific mitigation opportunities, meaning that it's not just about the port and the resilience of, supply chains and the infrastructure side of it, but some economic sectors might also have a buy-in to having a resilient port in that region, or just investing in climate resilience. Namely, here, we notice agriculture and chemical manufacturing sectors are the ones that suffer the greatest loss and are the ones candidates for the highest savings in this. And so the result here is intuitive because a lot of those grain and chemical products are actually shipped along the upper Mississippi River due to the proximity to the farmlands in that area. So I have a couple minutes I need to close, so I'll just close by saying that we already know that it's important to invest in climate resilience, but we need to show it in numbers, and we need to convince people to do it. And so this is kind of what I presented here, is that we need to think differently about how we're quantifying the return on that investment. It's not just another benefit cost analysis. It's much bigger than this. We need to look at the bigger picture, the system level, the other systems that are interconnected. And we also need to think about the person, the individual decision maker calling the shot, making the decision to invest. They are also influenced by that social dilemma and these decision biases. And so we shouldn't discount these. And this is, in fact, mentioned, like I said, in various reports, among them the NIBS reports, which mentions the kind of that discrepancy or this gap between builders being the ones bearing the cost, but then someone else is benefiting from it. We saw this with the port infrastructure, Tennessee having the port, putting into investing in a resilient port, but Illinois is the one really benefiting the most. What's next for us? We're going to put all of this together and determine a way to discount all these future losses or future mitigated losses into investments today. So what is the dollar amount that I need to invest today so that I can realize these benefits in the future? And so this requires a different way to think about the way we discount cash flows. The way we do it now traditionally is related to the physical risk of the infrastructure. What is the risk that the infrastructure doesn't perform as expected? Whereas we need to actually separate this from climate risk, meaning that if the infrastructure doesn't perform, what is the impact on the region? What is the impact on the other economic sector? All of this has to be built into the equation to ensure that we're incentivizing investors into buying and putting in money towards resilience and adaptation. I would like to acknowledge the financial support from a couple of agencies that supported various projects throughout this work. The U.S. Department of Housing and Urban Development through the Tennessee Department of Economic and Community Development, and as well as the U.S. Department of Transportation through the Maritime Transportation Research and Education Center. And our fantastic research team, Paul Johnson is a research scientist, and he led much of this work actually throughout his PhD dissertation. Our colleagues in civil engineering, Mark Apwitz and Craig Phillip, as well as a recent addition, Celine Wahib, who's a PhD student in civil engineering. With that, I thank you for listening. Here are the papers that I presented today, and be happy to take questions.